20K, 90% success.
All right, so today we start with threading and multiprocessing. Last time we did coroutines. We're going to go one level down, and then every lecture will basically do another level. Today we'll start with basic stuff. So how to start a thread, how to join a thread, how to do the same with multiprocessing, how to exchange messages between different processes. And this is basically what you need for 95% of what you do with multiprocessing. We will see more advanced stuff next time for memory synchronization and so on, but you don't actually need it to do most of the stuff you need to do with multiprocessing. So what is threading? Threading is one of the libraries used to process parts of the program in parallel. And in particular, the threading is a very peculiar thing that you can execute only one instruction of Python at a time. So if you have competing threads that want to access the interpreter, only one can. And so if you're doing computing intensive stuff, you cannot do it in parallel, right? So this is useful still for all the AI resource intensive things that are not accessing the interpreter, like for example, IO for accessing data over the network, or sending messages, or doing anything that is not related to the CPU to the interpreter. The advantage is that these threads are very lightweight. So it doesn't cost much to create one, it doesn't cost much to dispose of one, and the communication between the threads is simple, right? So this is the other advantage. So you wouldn't want to use other techniques if you just want to use asynchronous IO, for example, right? It doesn't make sense. How do you use threads? You basically can initialize a thread. You override basically the class thread, and then you can initialize and override run. So you prepare your thread with init, then you write in run what you want to execute. You don't override any other methods. That's important. And you can add your methods to the class as you like, and you call them in run. Then when you want to start it, the thread comes equipped with a start method. And this basically is a non-blocking method that starts the process and then leaves it to another thread. And when you want from your main thread, from your main program, you want to actually wait for the thread to be finished. So you want to rejoin it, you actually call join. That's a blocking method that will block your main thread until the thread is finished. So just to make sure we understand, that's the life cycle of a thread. You start by calling your start method on the main thread. This will, on the child thread, will run, which is what you wrote for it to run. And then on the main thread, at some point you want to join it. It will wait for the end of the thread, for the end of the process in your run function, and only then it will continue with the next statement. Clear? Yeah.
So what is the difference of main thread and child thread?
So the main thread is your program. It's where you start, you do the things that you want to for preparing the data, anything that you're doing in the main part of the program. At some point, you want to start a parallel execution of some part of your code. You encapsulate this in a thread, and then you start. At this point, this is the touch execution that runs in parallel, and it does whatever you wrote on your function run.
But shouldn't it be like it starts after this t dot start in the main thread, and then this self dot run will start it for the child thread?
Yeah, that's exactly what it does. So you start it with start, and then at this point, there's some other code in your main thread. You go on with that, and your child thread goes on with whatever is in run.
I think this in this blocking, I think it's starting running immediately when you start your program.
Yeah, I mean, first start.
Yeah.
Once the start is done, then the runs is executed. Once that is finished, actually the joins the join, you can call it, but it will block your main thread until the run is finished. Okay. Once the run is finished, then you will execute the next line in your main program, right? Yeah. So you need to join all your threads, or if you, you can also not join them. If you finish your main program and you quit it, if the threads are demons, set as demon, then they will be terminated. Otherwise, it will just stay there forever, and you have to kill your program, right? So, yeah, I mean, this is basically the main functionality of a thread and what you need to know about starting, joining, and making new threads. This is how you actually call them. You just import thread from threading. You create a new class, overriding thread. You define your run function, and then you create your thread. You start it, and then at the end you join it. And this between here and here, the run will be executed. And in between, you can do whatever you want on your main thread. This will not interfere, except if they're using at the same time they're using the interpreter, right? Questions about this? Is this mechanism clear?
So what's the difference between this and the sub process?
We'll get there in the next slide. All right, so multiprocessing is basically the same thing, except that, yeah, it's also used to process different parts of the program in parallel. But the difference is that multiprocessing uses OS level processing, and which means it uses fork on POSIX systems, and it spawns actually complete new processes on Mac and Windows, which means that you have to be careful what you do, because depending on the platform, it behaves slightly different, right? And is not as lightweight as threading in Python. In particular, it takes a lot more time to spawn a new process, to release a new process. And it's actually useful when you have very intensive CPU operations you want to perform, and you're not creating and disposing of processes continuously, right? We'll measure them. How much does it take to actually spawn a new process in threading and in multiprocessing? But when you have actually to do parallel computing, this is what you want to use, right? So the nice thing is that they have exactly the same interface. I mean, not exactly the same interface. What we're doing today, it will have the same interface. So you implement your run, you have your start, you have your join. It's exactly the same life cycle as a thread. So if you have implemented something with multi-threading, you want to implement multiprocessing, the jump is not really hard. Just change thread with process and you're done. Almost. The implementation is similar. The only difference you have is that you have to introduce this check, which seems like a bit of magic. But what it does is it checks that your process that runs this code is the main process. The problem here is that when you start a new process, particularly if you spawn a new process in Mac or in Windows, this file will be read more than once. So in your main thread, you want to execute this. Your main process, you want to execute this. But once a new process spawns and you read the file again, you don't want to re-execute this, because otherwise you'll be in a problem, right? You're going into an infinite loop. So that's why you always have to put this. Then you're fine, you're protected, because every time that it spawns, the Python spawns a new process, you will have this not as main, but as MP main, and then you're fine. It doesn't execute it anymore. But for the rest, it's the same interface. No difference. You can basically override process instead of overriding thread. You can redefine yourself and run, and then you can just use start and join in the same way, right?
What is the variable name here referring to?
This is a global variable that is defined in your process, and it basically tells you if you are in the main process or if you are in a separate process. Okay, so it's given to you by an interpreter.
Okay, maybe we will have example later, right?
Yeah, but
Okay.
we will actually see what's inside the name variable in concrete.
Okay.
All right, so this is pretty simple, right? There's nothing really to know about it. So how do we send messages or share information between threads or processes? There's many ways. I want to start with the easiest today and work through a few as example how to use this. And then next time we will actually look at something more low level, like locks and shared memory. But for now, we're using messaging. The idea about messaging is that you have something that is thread safe completely, and you share a piece of information. You produce this information, you put it in a queue, and then you consume it on the other side. And this is always thread safe. So you don't have to care about locks, you don't have to care about race conditions and anything like that. So what are queues? But first of all, queues exist both for threading and multiprocessing with minimal difference. There are some differences. Basically, multiprocessing has been modeled after Q, which is the threading version. It doesn't implement everything that the original Q implement, but for what we care, they're basically the same. And what you do with queues, you basically have messaging channels that enables you to exchange messages between threads or processes. So the way they work is basically you have the possibility to put a message. Putting a message is something that is not blocking, so you can just put a message and move on. The queue will basically collect this message, and then on the next process or any other process that has a reference to this queue, you can get, which is a blocking. When I say blocking, it means that when you execute this, if it doesn't return something, it will wait until it does, right? Which is a blocking instruction that waits for the queue to have something inside. And once it has, it produces as an output of this get, right? So you can imagine this is quite easy then to deal with multiprocessing. You want to share something from one thread to another. You just share a common queue. You put the message in one side, you get it on the other, and you're done. And you don't care about locked race conditions or anything else. Yeah, and the nice thing is that it doesn't have to have two actors. You can actually have multiple producer, multiple consumer. A consumer can be a producer, so you can put and get independently, right? It's very flexible. It's just a sink where you put stuff and somebody at some point will get it. It's FIFO unless you define otherwise. So first in, first out, and very easy to use. Questions about this?
There's only one consumer can get the message, not multiple consumers.
Once you get it, you remove the message, and therefore it's not there anymore. Yeah. But we'll see how to deal with this in the examples. So how do we use queues? Now, today we'll see one particular way to use queues, which is typical setup for data processing, for example, for distributed computing, which is a ventilator worker sync. So you have something that produces problems and needs to share these problems with some workers, which is our ventilator. Right? Basically has access to the data, has access to the whatever neural network you're working with, updates the neural network, shares again with the workers and so on. You have workers, which are basically responsible for different CPUs or different GPUs or whatever you want to access resources with, or just they're working on different cores. They don't know what the ventilator knows. They just receive a problem, they work the problem, and then they send the answer to the sink. So the sink is basically where you collect the results and then save them or use them somehow. You try to pass it to a simulation. I don't know. There's basically a different lot of things that you can do. The ventilator and the sink could be actually the same program. It's really up to you. But the point is, this detaches the collection of the data, if you want, and the knowledge of how the data gets organized and distributed, and this simple operation of, for example, inferring from the data the result or computing some result. So you can program this completely independently. The only thing they share is a message in between. And then you can share this with this message different things. For example, the data that needs to be processed, but also updates. If you have here in your network, if you want to update the weight score, you can also share it through the queues that you use for the data, right? Or you can send a termination message, for example, right? So, and the sink doesn't know anything about all this. It just knows once I have a result, I have my job to do. Right? So it makes your program a lot easier to read if you have something like this. And it uses queues very efficiently because you put your data from the ventilator, you get them from the worker. Once you're done, you put it in another queue for the sink, and then you get the next one. So it's a first come, first serve for the workers. The workers gets a job, finishes, put it in the sink, waits for the next. If the ventilator has not job to send, it will get done, otherwise it will wait. So everything is auto-regulating. Any question? All right. So let's start with the interesting part. See if this works. Yes. Okay. Let me first select. How about? All right. Let's first look at the code. So I have better. Okay, I have just an helper function here to measure the performance of the function. So just ignore it. This is just a decorator that I have here. I don't want to use import, so I'm just copying it in the code. So you have everything in the code for later if you want to look at it. I'm just importing thread and nothing else. And here what I'm doing, I am looking at my thread. In the initialization, I just initialize a variable, max count. And this is very similar thing than what we did with class decorators, right? You select, you collect all the data that you need for your run in the init, and then the run goes without arguments. That's a general thing you want to do. You don't want to have to pass argument to the runs because you're actually initializing the thread, and then you're just starting it. And you don't want to pass arguments again, right? So you separate the initialization from the run. It makes reading the code easier. It makes also using the run then later easier. And if you want then to update something, then you use messaging, right? So you don't run is always without arguments. So I mean, in the run, I'm just doing some computation that is not really interesting. Is the usual plus minus of numbers, so that we can get some performance measurement. Then we start for threads, and we just
at time IT here is the decorator, right?
Sorry, time. Yeah, this is just a decorator. Every time you run, you run, it will basically print how much time it took to run.
Okay, just make sure that I'm remember correctly. Yeah.
So it's this decorator up here. It's nothing else as wrapping the function into something that prints the time at the end. And then what we're doing was just going through the threads, starting each of them, printing that we started. Then we wait on the first, right? So what happens here? We start all of them because this is non-blocking. So start the first, start the second, start the third, start the fourth. Then we immediately go here, and then we go to the first and we join. Once you run this, this is blocked until the first thread, not the first in general, but the first in this list has finished. Once this is finished, it will print completed thread 0, and then we'll go on and then wait for the next. So if the next is already finished, then we'll just join it immediately. Otherwise, wait for it to join and so on, right? And then it will finish. Make sense? So.
And the third finish before the second is joined.
The third can finish at any time, but it will just end there. I mean, the join will then capture it. So the thread can be alive or can be not alive, right? And you can also check if the thread is alive, for example, and loop through them until you find one that's not alive and join. You can also do that. In this case, I'm just hardcore waiting for the first. And once that is finished, it's not alive anymore, then I'll join it and then wait on the second. And the second could be either finished or not. Okay. If it's finished, I join it immediately. If it's not finished, I'll wait for it. And then I go to the third and so on, right? So let's run this. Oops. Doesn't like me. Okay. So it's starting all three, as we know that it should do, right? And then it completes them all at the same time in about 10 seconds. And so it's waiting on the first. At some point, the first is finished, then it jumps the second and third almost immediately because they either are already done or not, but basically it shares the CPU among the three, right? So you know already, because we saw this in coroutines, this is not actually running in parallel. This is blocking the interpreter, sharing the interpreter across the three threads, and using it alternatively. It's not really doing the computation in parallel, even if it seems, even if they're ending all at the same time.
But when does it switch between the threads? Because was there any blocking time in that?
I don't have any blocking time. This is up to interpreter. You cannot expect it to act in any particular way, right? We'll see what happens with multiprocessing. Is taking 1/3 of the time. Any question about this?
A difference. So you can also instantiate threads with this threading the thread target to some function.
Yeah, well, you can, instead of implementing the class, you can actually tell it what's the run function. But it's the same. It's like if you put the run, your function that you're targeting with you can do the same processes. If you put the function inside the thread of subclass as run, it's one-to-one the same, right? What this initialization does is just basically putting this function into the run and then the user start. All right. So
is there a way to know how many cores we use when you run this?
one.
Only one?
Yeah. Because again, you have the global interpreter lock. So you can take for granted that when you are using threading, it will never use the CPU on multiple threads at the same time.
But are they using the same core, or sometimes you jump into another?
That is up to the operating system. You don't know that.
But the CPU utilization is only 1%, 100%.
It will not go over 100%. I mean, unless you are using C libraries that are bridging to Python that are doing multi-threading behind the scenes. That can be like if you're using TensorFlow, you don't need to use multiprocessing, but it's going to run in parallel if you set it up to use multiple CPUs, for example, right? But that's because it's done inside the libraries. You don't have any control on that. If you want to run your Python code on multiple CPUs with threading, you'll never be able to do it because of the global interpreter lock. Okay, so I'm sorry I had to use PyCharm and not Pythonista, so it's a bit less readable. But the problem is this: you cannot run multiprocessing on Pythonista because Pythonista is a iOS program, and multiprocessing using OS level processes, which are not allowed in iOS, so you can't use it. Period. But yeah, so we're going to deal with this like this. So what is in multiprocessing different? As you see, it's basically the same stuff with slightly different. I am doing my same time it. I am actually, ignore this. This actually shouldn't be there. Otherwise, I'm just initializing my max count, and I am running, doing the same thing with timing. And in the main script, I'm printing my underscore name underscore just for documentation. And then I am running my stuff inside an if name equal main. But that's the only difference. Otherwise, I actually kept the same name, sorry, threads, there's processes. But otherwise, I'm just doing start and join. And I'm doing the same stuff, right? Pretty easy, right? So there's nothing particularly difficult about multiprocessing. It's just the same stuff as threading. So let's run it. And yeah, doesn't want to do that. No, I'm sorry about this. Let's do it. I know how to do it. Right. So let's scroll back. Let's go step by step. I start my main process. I arrive at this print, right? And then main is equal to underscore underscore main, because I'm parsing the file for the first time. So now I start my first process, my second process, my third process. I'm here. Once the start happens, what multiprocessing does is goes through this file again, and again. And then it prints again 3 times. This time is MP main, right? So it parses again all the function definition, process definition, and so on, but it doesn't run through this because I'm checking. If I were to exclude this, and actually we'll do it, you'll see that it has an exception for you, which tells you that you probably should check your spawn strategy and you're not using fork and so on and so forth. And that's basically where threading and multiprocessing are different. This is very OS dependent, right? If you do it in Linux, you will have completely different behavior, right? But if you use this, you're going to be protected from this because this is then predictable. It will run only on the main process. But otherwise, it's the same thing. Now, the difference is that we got everything done in 3.5 seconds instead of 10, right? And this is the difference between multiprocessing and multithreading, as we saw last time with coroutines. Multithreading does exactly as coroutines, it just runs switching the context between the 3 threads, but using only 1 CPU. Multiprocessing is actually doing this in parallel without any problem. Any question about this?
Why does the visual process run through the full file?
Because it's implemented like that.
Because you define your run function up there.
Yeah, but it when it spawns a new process, it basically re-goes through the Python code.
Okay, if the class was in another file, would it then still go through this file again?
It would go through the files that, I mean, you have, what happens in C when you put an include? Just dumps the file there, right? Well, that's basically what is happening here. I mean, if you have an import, it will reparse your import, right? We'll just go through the Python definition of what your code again. So you have to be very careful what you do, because you don't want to execute this instruction 2 or 3 times. And the only control you have is this variable name. So that's why you do this check, because if you didn't have this, you would actually execute this instruction multiple times. Actually, let's do that. Let's remove this, indent this stuff.
Could you say for each process it spawns a new interpreter? Right?
Sorry? Yeah,
Windows.
absolutely. So with fork, it's different. I don't really know what's happening under under the curtains. But yeah, so if I run this now, let me see that I use the right command. And yeah, we got a little bit of a problem. So what's happening here? A lot of exceptions, right? So if you see, it's using multiprocessing spawn because I'm on Mac, so it's using spawn and not fork. And then it's telling me somewhere down the line that an update has been made to start a new process before the current process finishes bootstrapping phase. This probably means that you're not using fork to start your child process, or you have forgotten to use a property item in the main module. If name main equal free support. Basically, it's telling you you're doing something that is not supposed to happen. You should use if name main, then do, otherwise not. And you're running into a loop. So lesson learned is don't forget the if name equal main, because otherwise you run into problems. But except for that, the rest of the interface is pretty easy. It's like the same as threading, right? You can actually forget about all the low-level differences at OS level because you not encounter main problems with this if you stick to queues and processes. Make sense?
Maybe comment on the import, because I tried this once.
Mm-hmm.
The TensorFlow worked in a different process. If you import TensorFlow at the main level, then it imports it for every process. And the first one takes all of your GPU memory, so the second one dies. So if you move the import to the one process, then it actually works.
But you can try like the GPU along with the memory stuff, right?
I'm an expert at TensorFlow also. But if you move the imports, it also works.
Yeah, I mean, if you importing something that is not just the code definition, but is doing something actively, and there's many Python libraries that do that, multiprocessing can be a bit of a pain. Because then you're actually executing stuff multiple times, and it's platform dependent. It's platform dependent again, right? So it really means you really need to check what's happening on Windows, on Mac, on Linux, on whatever platform you're running.
Also, another question.
Yeah.
So let's see, you have three like process.
Mm-hmm.
Then you wanted to load some file from your local memory and do some maybe operations on this local memory.
Mm-hmm.
If you are using the multiple process, which means you need to, for each process, it will load every, you need to load 3 times for the
We'll see one example of the ventilator worker sync paradigm. And that's one way to deal with this. So you have basically the ventilator loading the file and then splitting it up, sending it to the different workers, because you don't want to process the same data on each worker, right? You want to split the data probably. And then the worker will work on the data and then send the result to the sink. That's one way to do it. There's other ways. You can use shared memory, you can use manager, but we'll see that next time, right? So yeah, I mean, that's basically what you need to remember about processes. So let's look at queues now. So for queues in threads, it's it's quite easy. I mean, this is just a very simple example of how to use a queue. I mean, ignore the time it, right? I'm just initializing my thread. I'm setting up the queue in the int. And this is a typical thing. You want to define the queues in your main thread. You want to pass them to your executors or workers or whatever child threads. And then you want to use the same reference to pass messages between them, right? So you only have a direct connection before you start the thread. After you start it, you only use the queue to communicate. And what you do then in the run, well, what I'm doing is just I'm putting in the queue that I've initialized it, right? And that's it. And then I sleep 1 second, and then I end my my thread. Sorry. In the main code, let's put a space here. In the main code, what I'm doing is I'm creating my queue, then I'm creating my thread, passing the new queue, and then I'm basically running it by starting the thread, getting the message. So I'm blocking here. Not really. I actually have a timeout of 0.01. So this is a case where it's not blocking. It will give an exception if the message is not there. And then I print the message.
Wait, do you give an exception or just return one?
It gives an exception. So you have to try accept if you.
Is there also a try get function?
I didn't check, but I usually use try, get inside, and then I just accept pass if I don't care about the exception. We'll see an example in the processing where I did it. Here it's not relevant. We'll see why. Because it's very fast, right? That 0.01, it doesn't really need it. But if you were doing with the process, it would give an exception.
If you would flip 22 and 23, then it will give an exception.
Yeah, absolutely. If I would time sleep first, it would give an exception. So then it prints the message. And when I do run, we'll see how fast it is. Then I do thread join. And then I'm done. Right? So you'll have basically 1 second between the printing of the message and the done. That's what you expect. Because I'm collecting my queue message, I'm printing it. And then the main thread is, the child thread is waiting 1 second. And then it will should join and press and print done, right? So that join, because join is blocking. Is the logic clear? right? Okay, so let's do this gimnix. Yeah, I can do that because I have 6 of them and it only supports 5 in the. All right. So it took, help me out here, 200 microseconds. Right, 200 microseconds to what? To do what? Can help me. What did it do in 200 microseconds? Anybody? Where do I start? Where do I start to count?
With run,
With run.
because the start, it is called by start from the.
So it calls the start, right?
Yeah.
Then it queues the message and it prints it. So it means that it initialized the thread, started the running, and it queued the message into the queue. And that took 200 microseconds. Right? So it's pretty fast, right? I mean, you can basically start threads anytime you want. You won't see a dent unless you run them 1,000 times each loop, right? I mean, it's pretty lightweight. And then it waits a second and prints done, and we're done. And that's why you don't get this to accept, to do any exception. I could do is also blocking, wouldn't make any difference. But if you do it with timeout, let's do the experiment before. Mirko suggested. So now, if I remember the right key combination, there we go. Queue is empty. So when you actually get with the timeout, it will wait for that time. If the queue doesn't have a message, it will accept out and the error out and tell you that the queue is empty. And you can check for this. If you want to check, you know, there's 2 ways to check if the queue is actually as something. You can if queue empty, or you can try and pass on the accept and move on, which is something that you do pretty often in Python. You don't actually check something, you just try to do it because it doesn't hurt it. It will do the same. It will just check if the queue is empty or not and pass the message if it's not. So
I'm pretty sure there's a try get function. It just be except.
it could be.
Which is just prettier than try except.
Yeah, try accept is fine. All right, any questions about this before we move to multiprocessing? You're good? Okay.
What can you put in queue? Anything, any objects, whatever you want?
We'll see that. So let's wait. Let's go to queues in multiprocessing now. And let's see what this is all about. So again, not much of a difference. My time it is still there. And for the rest, I still use the same variable names. As you see, it complains probably because I called it thread. But yeah, I'm initializing the process with a queue, as in the case before. I am setting in run the message in the queue, and then I'm sleeping for 1 second. Then I have, of course, to check my if naming. I don't know why this is indented like that. I mean, it still works, but it sucks from a perspective of design. So I initialize my queue. I initialize my process. Sorry about this. It's a process. And then I am defining my run. Now here, I'm doing something a bit special, yes. So instead of just getting and printing, because this will be throwing an exception, I am polling the queue, right? I could actually do a queue get and block it, but I don't want to because I wanted to show you something different. Because we'll use this when we have to poll different producer, for example, for any results that's around, what we'll do, we'll check, for example, a queue, and then if there's nothing there, we'll check another queue. And then with nothing there, check another queue. We can do this. So you can poll different queues in the same process. And this is, it's okay because checking the queue is pretty lightweight. So you can do it every, 10 milliseconds, nobody will notice, right? And yeah, if once I get it, I'll print it. Otherwise, I'll pass, move on, try again.
If you call q.get without the timeout, is it busy blocking?
No, it is blocking the thread, but it's not busy blocking. It's not blocking the interpreter. Right. So, any questions before we run it? Give me times or the gimmicks again.
There's a shortcut to run exactly the one that you just opened.
Yeah, I didn't find it. All right, so let's try this again. And what's the difference? Yeah, 0.05. So this is 50 milliseconds. It's not 200 microseconds. It's 2 orders of magnitude more, right? A bit more than 2 orders of magnitude. So lesson learned. If you're starting processes, it's heavy. So you shouldn't do it in a loop. Just, every time you get the data, start the process, pass the data and work with the process because this will slow down your program. What you want to do is start the process or use a process pool to actually always reuse this ongoing process. Because what's going on behind the scenes is that each of these processes is spawning an OS level new process, which is heavy. And if you want to know more about this, you can ask Andrea or Alex because they know more than me. So, but basically, it's not something you want to do in a multiprocessing to starting always new processes. For the rest, it's pretty much the same. The only thing that we needed to do is do this because if we don't do it, we get the same exception as we did before. Queue is empty, right? We could have blocked it and just wait for it. That's the same. Simple, right? Okay.
So what is the slower is obviously starting the process, but is the queue also slower between processes? Probably, right?
It's probably a bit slower because there's a bit of locking going on and multiprocessing, shared memory, but I didn't measure that. You can take for granted that anything you do with different processes is always lower than doing it with different threads, because that is done by the Python interpreter internally. And in the other case, you have to bridge actually 2 processes and then go through the interpreter again. So it's going to be slower, bound to be slower. But it's compared to starting the process itself is actually irrelevant.
Can you try this if you move the thread and start outside of the run function?
Yes.
No, it doesn't.
You want to move this outside of the run function.
Yeah.
So let's try this. That's fair, right? Should work. I don't see why it shouldn't. It does. Look at that.
It's 3 milliseconds.
It's 3 milliseconds. Actually, the queue passing is pretty heavy.
No, it's not, because there you're just starting the start on the other process. But
Right, it's non-blocking. Yeah. I need to do something inside here. You're right. So we need to do something with thread, like
why not start with
no, you can't do that. I was doing with the message queuing exactly, because I know that is I know that if I get from the queue, it means that my process is through with putting it.
Send 2 messages.
The only thing that I can do is actually, yeah, okay, send 2 messages. That's fair. So my message is non-queue, and then in here, where is it? some file Q. Let's, oops. Send to, then we do this.
But you only want to run one machine at a time.
Actually, I want to get to. So I am reading the second, and then I can do the difference between the other run, which was 50 milliseconds. So we'll see what time it takes to actually read two. Make sense? So yeah, 10 milliseconds, give or take. Right, so it's heavy.
Run it again. Yeah, maybe we should run the other. Oh. I think you need to run.
Yeah, we need to take a statistical sample here. But okay, I mean, the point is the main thing is starting the process, right? You saw that. And then we can do statistics if you want on the message and sending on the other side. But the point is, in the case of threads, it was just a totally completely different order of magnitude. It was microseconds. So it's pretty clear that everything you do in processing, whether it's starting, passing messages and so on, is just heavier. So it is worth it if you have to pass few messages, do a lot of computation, and then pass the result at the end. Then it's worth it. If you're just passing information around and using a light part on the CPU, then it's a lot better to use threading. If you're doing asynchronous I/O, you should use threading. You shouldn't use processing, right? Because the work of starting a new process and passing the information is just a lot more than what it takes to actually get the information out of the file or of the network. All right. So shall we move on? Oops. All right. So next one is our beloved ventilator sync, worker sync process. So here we are doing something a little bit different. This is a bit more complex, and it's still a toy problem. It's just computing this odd sum of numbers. But what we're doing is we have three classes here. So the worker, which is basically initialized with a queue in the input and a queue in the output. The input queue we're going to use to send the data, what it should solve. And the output queue is to send the result, right? So the data is actually the one integer, which is the range on which it should do this strange sum, right? So, and then the output is going to be this result. And the run is going to do something very simple. It's going to check on the queue, get the problem. If the problem is -1, that's our sentinel. Okay, sentinel is what you commonly use for terminating a process. What's called. If the problem is equal to -1, then we're terminating and breaking the loop. Otherwise, we solve it. So we start this function and then we send it in the out queue. Right? Just as simple as that. Okay, so, and this is also a good habit to do. Separate the logic of your problem from the management of the queues, because otherwise you're mixing two completely different things. You don't need to do that, right? So that's it. That's our worker. We don't care about who puts the data in the queue as read, what happens with the result. We just solve the problem. We get the next problem from the queue. We solve it. We put it in the out queue. We wait for the next problem and so on until there are problems. And then we terminate it. That's it. What's the sync do? The sync, well, it basically, first of all, it doesn't need an out queue because it's just getting the results from the workers. So that's all it needs, right? And it needs a timeout because the sync doesn't get to know when stuff is done. I mean, otherwise I would actually need to signal the sync as well for the termination, right? And then what it does is just waits on its own queue, and when it gets a solution, it prints it. You could be, I don't know, filling replay history buffer or putting it in some file or, doing whatever you want to do with the solution. Starting a simulation, anything. Yeah, it tries. If the timeout is too much, it sets break, gets out, done. Questions about the sync or about the worker? It's a pretty simple configuration, right? And it's something that you can reuse and just put, your problem here, your data here, and you're done. So the ventilator is the main thread. Ventilator is what you do in your main thread. It makes sense because you're actually starting the rest from here. Is the boss is deciding what the problems are and when to finish it. And yeah, what we're doing here is we're starting the two queues. So one is the queue between the ventilator and the workers, and the other is the queue between the workers and the sink. Right? Sorry about that. And then what I'm doing is I'm starting an array of workers. Just start as many as I want. I don't care. It's the same structure. If I have 1,000 or 2 workers, I still have only 2 queues. I don't have a queue between each worker and the ventilator, just one queue. It's used by all the workers, right? And they're all waiting on the same queue. Just first come, first serve. Whoever is done first will take the next problem. Then I just go through the works and start them one by one. Then I start to sync with a timeout of 5 seconds, right? And then I create my problems. And these are just, numbers that they need to add up together. And then I need to terminate all 3 of them. And it's clear that if I put 3 minus 1, because all of them are waiting on the queue, and once they get the first minus 1, they terminate, that will terminate all of my workers, right? Because they are bound to process each of them 1 minus 1. Questions on this? Why am I doing the architecture like this? Is it clear?
The only question I have is why aren't you putting the queue before starting sync and workers? Or
The queue, I need the queue initialized before I create the workers, before I create the sync, because I need to pass those queue as references.
Yeah, no, I mean the putting inside the queue. You could do it before starting workers and syncs.
Yeah, absolutely. I can put whatever I want there. There is a problem with this architecture. You can tell me what the problem is.
You need to put this value -1, so it's processes every time. So
First problem is this. So I need actually to know how many workers I have here and actually, put as many terminations as possible. That's a bigger one.
Okay, just show this. So could you use the workers to put the -1 back into the ventilator?
Fantastic idea. Yes, you can use it as a token
Yeah.
and just put it back. What's the problem then? At some point, what's going to happen? I'm a worker. I take the token, right? Terminate myself, put it back and terminate myself. The token is back in the queue. Next worker does the same. What happens?
The last one does the same.
Put it back in the queue is filled. So you have to clean up the queue at some point. But it's a bit of a cleanup that then the ventilator or the sink need to do, right? So you have to work at some point with some timeout, because you need to clean up the queue or terminate it or do something, right? Unless you actually know that all your workers are done. So you need, in any case, to register your workers, to manage your workers. You cannot just leave them to be, unless you know that you can deal with a timeout. So, but either you use a timeout or you use a register. You have to do one of the two. But that's still a bigger problem.
You start the sync before you start the actual work on the workers.
That could be a problem if the workers are slow. So the sync could actually terminate itself because of timeouts. But I'm pretty sure that if you put a timeout, you want to put like 3 or 4 times what the typical workers is, or maybe even more, because this is probably a long lasting process. The problem that I'm mentioning is what if this list is very long? What if you have to parse a file of several gigabytes and put this in the data inside? How would you do that? So you start the ventilator and you parse a file of several gigabytes and you start tuning this. What happens at some point? Full. The queue gets full, right? And then it accepts out. So what you need to do is actually pace yourself. You need to actually check, and I didn't do this, I didn't do the example, but what you need to do usually in real life is actually either have a max queue and check, the count when you put and when the sync it removes the counts, and so also you have some state machine that comes up or down, or you can check if the queue is full and then only put it if the queue is full, if you're confident that your full queue doesn't remove too many resources from the rest of the processing. Because of course, I mean, if you have very large data that you want to put in the queue, you might not want to wait until the queue is full. If every data point is 1 gigabyte, for example. Right. So there's a bit of management to be done here, but in general, this is the simplest way to deal with this, plus some management.
Put throw an exception when it's full.
Yes, same as empty, same as get empty, put full is the same. So then what I do is I'm done, because I just when I'm done filling my queue, I just go to the workers and I join. Now wait for the first to be finished, then the second, and the third, and then I'm done. Then I wait on the sync. I want to close that too, and then I'm really done. Questions on this?
Actually, I found the answer to my question that I had before. Putting the processing queue after starting workers and sync means that the workers can start working on the queue while the programs are being put in.
So the worker, if you saw what the worker does when it starts, it's here, right? So until the queue is empty, the worker is going to stay here, no problem. Literally, no problem. It's going to wait until it finds a problem. When you first queue your first problem, when the queue has a lock, right? Behind the scenes, what's a queue? I mean, there is a global lock on the queue. If somebody wants to put something on the queue, it locks the queue, puts the message, removes the lock. Then there's basically some other people waiting on this lock. The first one that gets the lock reads the first message and then releases the lock. Right?
So while the for loop is putting problems in the queue, the workers are already
exactly. Once the first is in, the first lock is released. Somebody gets the lock, gets the first message. Then I don't know if somebody else gets to check or not, but at some point the ventilator will be able to put the second one, and then the another one will get the lock, get the second message, and so on, right? And it will go on. But there's no problem there. It's not the only thing you're doing is you do your program with the idea that something will come, and you just wait. And once it's come, you process it, you put it in the result queue, and then you wait again until you're done. And the only thing you need to check is the sentiment. If the sentiment gets sent to you, you break your processing and you exit. That's it. Right? It's very simple. I mean, that's why I like this paradigm, because it separates very well the different things, and you don't have to deal with all at once. You have to deal with just your problem there. Shall we run it? Yeah.
So if I want to know, we have one problem, maybe problem 1, 2, 3,
Mhm.
and I want to know what is the solution of a particular problem. So let's say I want to know the solution of problem 1.
Well, you can just put in the queue something that has both the problem and the solution. Then the sync will get the collection of problem and solution, and you will do with it whatever you want. But that the right thing to do is do it in the sync, right?
Okay, but I like having an assignment between the queues that you can.
You don't want to do that. You don't want to do that because this will actually bind your code, right? Then you will have interdependencies and stuff gets complicated. You want to decouple as much as possible. The worker knows only one thing: I have to solve the problem. And that's what you want the worker to do. You don't want to do management of data in the work, right? But you can do it in the sync. You just pass on the problem. That's it. Shall we? So let's run this guy. And so it's doing our sums and then terminating the workers. Let's do it again like this. I'll find a better way next time. So you see, it's doing in sets of three, right? It's doing the first three, then it's doing the second three, and then slowly it's terminating each of the workers. Because I'm waiting on the first. Once the first step is done, I'm terminating it. I'm sending a -1, terminating it, and so on. And that's basically what happens. But it's not guaranteed. And this is probably why you see the terminating worker here and not down below. It's not guaranteed that each worker has the same amount of work as the next one. Because I'm starting the first worker, is already reading in the queue while I start the second, and it takes time. So it might be that the first worker is already processed the first, already put it back in the sync, while I still firing up the third worker, and it's getting one more thing. So it could be that I get to the -1 first on one side and on the other, right? Anyway, the order of a processing and so on is not something you should be concerned when you do this. You just know that you throw stuff at the workers and somebody will pick it up. And that's basically how you should design your code. You shouldn't plan for the workers to act in certain orders or with certain synchronization. When does this cause a problem? Any idea? So let's say that my solver needs to be updated. Like for example, is a neural network. We need to change the weights. I could just say, okay, I'll change the weights at some point, but sometimes I want to know which weights I use to solve some problem, right? So I need to actually synchronize them, block them, and then start processing them again. So we'll see one example now. I can do that. There are better ways to do it, but this is simple. It still uses just a queuing mechanism, and we'll see how we can solve problems like this in queue. Next time, we'll see how to do it in shared memory with locks. Okay. So unless there are questions about this now.
So for this, we could also more easily use map.
Of course. I mean, with pool.map, you can do a lot of other things, right? But I wanted to start from this part and show you this interface completely, right?
Quick question: is there any like limit size for the messaging in the queue? For example, we want to
it needs to fit in your memory.
Okay. If, for example, it's like 40 images, then it's just depends on your.
Depends on your RAM. Right?
It depends on how you define the queue. I assume there are parameters to pass into queue.
I'm pretty sure there are, but the point is the single message needs to fit in your memory, right? And that's the main important thing to remember.
The fourth thing is depends on how many single messages you have in this.
Of course, the queue, if you fill up the queue and it gets out of bound of it. So let's go to the next example. And let's see something more complicated. So this time I am defining my message in a more structured way. Instead of passing just an int, I'm passing a class, an object, actually. The object has three parts. The first one is an header, which tells me what type of object it is. It's a sentinel, so I'm terminating my process. Is a data or is an update? So the data is something I need to process. An update is something I need to update my internal state so that I can process next data again. And I'll be behaving on those three messages differently in the worker. So for the sentinel, I am going to, let's go with this. So for the sentinel, I am going to just break. If I get the sentinel, I'm moving out, right? Worker done. If I receive the data, I'm just processing the solution. Now there is kind of a thing here because I don't initialize my solver. So this filter is basically the core of the filter that I use in my solver, right? If I don't initialize it, I'm ignoring the message and I'm putting it back in the queue. I can't solve it. I'm not initialized, so I'm reading a message, but my filter is not good. Then I'm putting it back. I want to read because that's how I get the filter. But until I get the filter, I'm ignoring everything that is data, right? It's perfectly fine, right? So if I get the update, what I'm checking is if the output is relevant for me. So I have an ID, it's like a versioning, right? I'm incrementally incrementing my counter of the filters that are produced in the ventilator. So if I increment the filter and I pass it in the queue, every worker will basically update itself, right? And so if the last ID is equal to the message ID, so if I'm already at that update, I'm just putting it back. All right. But if I'm not at that update, if this filter is new for me, I'm updating myself. I'm consuming that update package. Right. So as a ventilator, I need just to produce n updates for n workers. And then each worker will consume only one, because once it's updated, we'll keep track that this is the right version. It's already at that version. We'll not consume another update. We'll wait until it gets data, right? It's clear, right? The mechanism. The sync is the same as last time. And what I'm doing here is I'm in the ventilator. What I'm doing is I'm going through a certain number of filters. And what I'm doing is I'm producing first one update message for each worker. And I put it in the queue. And then I'm going through the data. And I'm sending a message with the data in the queue. Once I'm done with the batch of data, I'm going back, creating new batch of filters, putting it into the queue, and then processing the data again. So this is a typical case where you have basically something that you want to update in like a neural network with new weights, and then you are processing the data. You're going through some history, for example, or replay history or somebody, and then you go back, updating again, going through the replay history, and so on, right? If we look at the solve, right, we see the general structure. What does this do? This is basically just put to sleep because otherwise it was too fast. And then it's using just a NumPy to do a multiplication of a filter, which is a 1000 by 1000 matrix, times a problem, which is another 1000 by 1000 matrix. So it's just the generic NumPy operation. Yes.
If you change your filter multiple times in the
Yes.
queue, then this doesn't work, right?
Of course it does. Why?
Because so if you launch 3 processes and your first one gets the filter, updates its filter, and the other ones are still busy, so it gets the next filter, and then it passes it back in the queue and it puts it in the back. And if there are new filters in between, then the others will update with the new filters before.
Right.
So you can't just from your ventilator queue up filters.
So you'll get out of order. You get out of order. That's right.
Yeah, so you can't do a bunch of filters, and a bunch of forms, a bunch of filters, a bunch
No,
of forms.
you cannot do that. It's completely right. You will not be able to perfectly synchronize it, right? Unless you have some timing that helps you there. But otherwise, you will not be able to perfectly synchronize it. You have to keep your queue short to do that. So, and that's true. And for that, you need actually a lock. For that, you need a shared memory, a lock, and to manage this in a different way. Or you need a separate queue. That gets a lot more complicated if you start having a queue for each worker like that. So the right architecture to do this is to have a shared memory and a lock, and we'll see that next time. But I wanted to show you how to use different messaging and how to use token-based things around in here, like putting it back in the queue and so on. So this is a mechanism, a tool that you can use. It's not the right tool to do this. I agree. Okay. So yeah, the process is very simple. It's just making a matrix multiplication. The run didn't really change. We're just checking for what kind of message we have and then processing it in the proper way. And I mean, again, a bit of good practice. If you have a type check, always check for also what if somebody passed something that is not appropriate. And the sync didn't change. And in the main, I'm just creating these random matrices and I'm queuing it exactly like we did before, right? So nothing new either here. The only new thing is again this processing, because I'm processing message queue, message queue. Shall we run it? So So what it does is what we expect. Takes the filter, process some, then updates the filter again, then process some, then updates the filter again, then process some, and so on. And at some point it terminates. But yes, as you see, you have out of order execution, right?
Question regarding update, like as far as I understand it, you just put some token in there and everyone checks, okay, I already got it out. If I already got the update message, I'll put it back, right? And
Yes.
so at some point, let's say this runs a long time and I update it sometimes this, sometimes that. Isn't there possible that the queue just fills in with like, so to say, that?
Yeah,
update
I mean, if you want to do this properly, what you
Yeah.
would like, what you should do is here. Once you're here, you should actually check if the queue is empty, right? You should do if ventilator queue empty, not empty actually, time slip, like 0.01, something like this. I don't know if this breaks, but the point is, sorry?
While ventilated, you know, MPC.
Yeah, that's a good idea. Wow. So the point is, you're basically waiting that everything in your data has been processed, and then you process it again. Then you don't care about the out of order there. You should actually do it here as well to block the data and the updates, and to synchronize the both all of them, right? So that's basically what you will want to do. So let's try this. Probably will break everything, but we know that.
If you just do it there, it's not that much. So just want to check that all of them updated.
Put the data. It could actually, yes, because they are at the end anyway. So I actually only need to check that the updates are completed before putting the data. I don't need to do it after the data. You're right. Right? So let's try again, and let's see the nice exception we'll get. Yes, I knew that. No such file or directory. Let's try with empty and not. Oops. Stop and rerun. Right. So now it's doing exactly that. It's updating them all at once, and then processing the data and so on. So, but yeah, I mean, there are better ways to do this, right? But the point is, what I wanted to show you here, first of all, you can pass in the queue whatever you want. An object is fine, right? And it's thread safe also for objects. You don't have to care about that. The second point is you can use token messages. I think that you pass along. I work with it, then I put it back in the queue. Next time that guy is gonna take it. I check it, put it back, check it, put it back. I can do that. It's totally fine. You could use also first in, last out for this. You can use a stack, right? This is probably more appropriate for this.
So it has to be plain objects, right? There can't be any references in the object, otherwise it will do some references.
And how is that any different in Python? Every object is just a pointer.
But if you have a reference to a number array that is outside, what happens? What will it put in there? The number array?
So I just put a number array inside, right? That's what I did. The payload of this is a number array. Where is it? So here, that's my data. When I pass the message, I basically go through my data there, right? So these are NumPy arrays, and I put as payload my data D. So I'm passing NumPy arrays inside. It's not a problem.
Yeah, okay.
Now, if something is happening at sea level with the library that you are importing, everything can happen, okay? But usually multiprocessing is taking care of most of the stuff for you. And it's thread safe. Any questions on this? Right, then guess we can stop it here. Next time we're going to share memory across the processes and use manager and see what locks can do. And basically go a little bit deeper than queues. But again, queues will probably help you with 99% of the problems you have in multiprocessing. And they are safe to use and you don't have to care about the rest. So I strongly advise to use queues if you can. Right? Thanks.